Welcome to Mrs. Z's Chemistry. Let's begin this video with a review of delta H by looking at the standard enthalpy of formation. These chemical reactions are synthesis reactions with only one product on the right-hand side of the arrow. The heat of formation, or delta H of formation, is always for the formation of only 1 mole of product. Here's two examples. The production of 1 mole of carbon dioxide releases 393.5 kilojoules per 1 mole of carbon dioxide. The negative sign tells us that this amount of heat is being released. Our other example tells us that the formation of nitrogen dioxide absorbs 33.2 kilojoules of heat. The positive sign tells us that this amount of heat is absorbed. Let's look at this example problem. Ozone, O3, forms from oxygen, O2, by an endothermic process, which means the process is going to absorb energy. Ultraviolet radiation is the source of the energy that drives this reaction in the upper atmosphere. Assuming that both the reactants and products of the reaction are in their standard states, determine the standard enthalpy of formation, delta HF, of ozone from the following information. Here we have a balanced chemical reaction and a delta H. What do we need to change, if anything, in order to make this a delta H of formation? Well, delta H of formations are for only 1 mole of product. In our original chemical reaction, we have 2 moles of product. So if we divide the coefficients in half for both of the reactant and the product, we have 3/2 of oxygen turning into 1 mole of ozone. The delta H then also needs to be divided in half. 286 divided by 2 is 143 kilojoules of heat that is absorbed for this delta H of formation. Before we look into the topic of 5.4, let's learn that we can add chemical reactions together. In order to do this, it's best to line up the arrows so that we can easily see the reactants are grouped together on one side and the products grouped together on the other side. Any compound that is both on the product side and the reactant side can be canceled. The compound must be in the same phase of matter in order to be canceled. Here we have carbon is going to react with 1/2 mole of oxygen to produce carbon monoxide. Then that carbon monoxide is going to be used up by reacting with another 1/2 mole of oxygen and turns into carbon dioxide. The reason this is a two-step process is that this overall reaction here actually does not happen in one reaction. It happens in 2 different processes or 2 different steps. Each of these processes have a different delta H, and then when we add the reactions, we also add the delta H's together to get our overall reaction. So let's go ahead and look at it this way. We're going to take all 4 of our reactants and write them out here. Then let's take the 2 products and write them out here. We can cancel the carbon monoxide on both sides of the reaction because they are in the same state of matter. However, we cannot cancel the 1/2 mole oxygen because these are both on the reactant side. So instead, we combine them together. 1/2 mole of oxygen plus 1/2 mole of oxygen equals 1 mole of oxygen. We're still left with our 1 mole of carbon, and on the product side, 1 mole of carbon dioxide. When we add our delta H's together, negative 111 plus negative 283, we get negative 394 kilojoules of heat that is released for this overall reaction. This is Hess's law. The enthalpy change, or delta H, of the total process equals the sum of the enthalpy changes of the various different steps, either 2, 3, or 4, or maybe even more steps for an overall reaction. It's important to remember that the delta H is directly proportional to the amount that we have in the balanced chemical reaction, according to the exact amount of coefficients that we have the way the reaction is written. So here's 2 properties of delta H that we need to remember in order to apply Hess's law correctly. Delta H is directly proportional to the quantities of reactants and products. Here we have this chemical reaction and this delta H. If we were to multiply every coefficient in this chemical reaction by 2, so 1/2 times 2 equals 1, 1 times 2 equals 2, and 1 times 2 is equal to 2, we also need to multiply the delta H by 2, which is why we now have a delta H that is double. And that's because we have double the amount that's being formed and double the reactants that are being reacted. The other product, or the other property, is different. Delta H for a reaction in one direction is equal and opposite for the reaction in the reverse direction. So to understand this, we need to actually understand that we can reverse a reaction. First, let's look at this example. 1 mole of hydrogen reacts with 1 mole of chlorine to produce 2 moles of hydrochloric acid, or HCl. This reaction releases 184.6 kilojoules of energy. Remember, the negative sign means the energy is being released. Now, if we were to take our products and turn them into reactants, so we take our 2 moles of hydrochloric acid and we break it down into its parts, 1 mole hydrogen, 1 mole chlorine, this process absorbs 184.6 kilojoules of energy. This is what is meant by the reaction in one direction is equal and opposite for the reaction in the reverse direction. We sometimes call this flipping a reaction, when we take the reactants and turn them into products and take the original reactants and turn those into products. We need to flip the sign of the delta H. So here's an example problem. Determine the enthalpy formation, delta HF, of iron 3 chloride, FeCl3 solid, from the enthalpy changes of these following two-step processes that occur under standard state conditions. Because delta H of formation is for a formation reaction, we want only one product, FeCl3, on the right-hand side, and we only want a coefficient of 1. In our second reaction, we have our product that we're trying to get to, and we only have it in 1 as a coefficient of 1. So let's not change either of these reactions. Let's just add them up. If you notice, the first process reacts iron with chlorine to make iron 2 chloride, FeCl2. Then that FeCl2 is produced, or once it's produced, it is then consumed with another 1/2 mole of chlorine to form our final product. These two compounds can be canceled because they are the exact same compound with the exact same state of matter. We're going to add everything else. 1 mole of iron. When we take 1 mole of chlorine and 1/2 mole of chlorine, we have 3/2 of chlorine. Now we need to add our delta H's. Pause and pull out your calculator to find the value of the delta H. When we add up the delta H's, we have a negative 399.5 kilojoules per mole. Here is another example. Chlorine monofluoride, which is this compound, can react with fluorine to form chlorine trifluoride. We do not know the delta H for this overall reaction, and that is what we are trying to solve. This overall reaction actually happens in 3 different steps, not necessarily in these order though, or in this process. We may need to modify some of these reactions, either by doubling some of the reactions or maybe halving it, so cutting them in half, dividing by 2 or multiplying by half. Or we might need to flip a whole reaction and change the products to reactants, reactants to products, and flip the sign of delta H. Pause to see if you can work this out. If you look at the product here of ClF3, we can see that that exists right here in reaction 4, but it's on the reactant side. It has the correct coefficient, so all we need to do to reaction 4 is multiply by -1, which means we're flipping the whole reaction and the delta H changes its sign. So let's rewrite these products as reactants. And then we're going to write the reactants as products. Because every single compound in all of these steps are gaseous, I'm not going to worry about writing the state of matter. Otherwise, you do need to pay attention to the states of matter because you cannot cancel unless they are the exact same states of matter as well as the same as well as the same compound. So there we have reaction 4. We are going to write a little -1 here by 4 to remind us that that's what we need to modify to the delta H as well. Now let's look at reaction 3. And notice that this CLF appears in reaction 3 on the reactant side, which is where we want it, but it has a coefficient of 2. So if we cut in half, or multiply by half, reaction 3, we will modify reaction 3 the way we need it to. So let's rewrite that, modified. We're only going to have a 1 coefficient. We're going to have a half coefficient here, a half coefficient here, and another half coefficient for this last compound. Now we have modified reaction 3, and we will later modify delta H in order to add up the correct delta H. Now we can see that for reaction 2, we have F2, our remaining reactant in the overall reaction, but it is on the product side, and it has a coefficient of 2. So we're going to, this is the modification we'll do to reaction 2, cut it in half, or multiply by half, and then we're also going to flip it. So we're going to put a negative sign out in front here as well. So we are going to flip and put our O2 and F2 on the reactant side, but then we're also going to cut them in half. So we'll have a half coefficient for O2 and a 1 coefficient for F2. On the product side, we now have 1 OF2 instead of our 2 OF2. Now, if we would add up all of these reactions, I'm going to change color here. If we add up all of these reactions, we can see that these are all of our reactants, these are all of our products. Let's cancel the things that are identical on both the product side and the reactant side. Something that might be tricky is realizing that half O2 and half O2 equals 1 O2. So that would combine on the reactant side, but we have 1 O2 on the product side as well. So all of our O2s can cancel. We have half Cl2O and half Cl2O on the product side. 1 OF2 and half OF2 would combine to 3 halves of OF2, which would cancel with this 3 halves of OF2. We have canceled everything that we can, and now let's go ahead and write out our full overall reaction. CLF plus F2 turns into CLF3. Double check that this reaction is in fact exactly what we want on this side as our overall reaction. Now we need to modify the delta H's. So looking at our modifications that we wrote over here on the side, we need to cut delta H for reaction 2 in half plus change the sign. For reaction 3, we need to just multiply by half. And then for reaction 4, we just need to change the sign of it. Go ahead and pull out your calculator and see if you can get the correct answer for delta H. Here is our answer with all of the correct modifications for each delta H. Here is one more example problem for this video. Pause to work this one out on your own. Here is the answer. These are the modifications. We did not need to flip any of the reactions, and we only multiplied the reactions by some integer rather than dividing any of them. And here, once you modify the delta H's, we come up with this answer.